This lesson is on techniques of evaluating limits. Hopefully, before you do this lesson, you have already had an introductory lesson talking about limits and what they mean. Recall that when we say the limit as x approaches, say, 2, means that the x value is getting very, very close to 2. And when we say that the limit of f of x is some number, say 5, we're saying that our y value, our function value, is getting very close to 5. In that first lesson, you probably did a lot of problems where you sort of found the value of the limit by using a table of values, perhaps, and you simply substituted numbers in that were close to the given x value and figured out whether y was consistently getting close to the same value or not. In this lesson, we're going to talk about other ways of evaluating limits. Notice here I have given you sort of a three-step process in finding limits. To evaluate, first of all, try direct substitution if possible. In your first lesson, you probably learned that many functions, such as polynomial functions, can have a limit evaluated simply by substituting the given x value into the function directly. That happens when these functions are nice, well-behaved functions. If that doesn't work, then you are down to choices 2 and 3. The second choice is to use algebra or trig to rewrite the function. And this second step is what will be the focus of our lesson today. The third step is sort of the last resort, as I call it, and that is to use a table of values to determine the limit. Now, I realize that in your first lesson, you did a lot of these limits by doing that table, but it is tedious, isn't it? So we would like to avoid that process if we can and find other ways of finding limits. What we want to concentrate on are those functions where we cannot do a direct substitution. Recall that any time our denominator becomes 0, our function is undefined, and therefore we cannot use a direct substitution. So you will see that in, I guess, nearly all of the examples in this lesson, we'll be looking at a situation where if we try direct substitution, we would be getting a 0 in the denominator, which is going to cause us some problem. Before we look at the first of our examples, I want us to look at a theorem that you may have seen already, but I want to talk about it a little bit more. This theorem says that we have functions that agree at all but one point. Let's take a look at that function and see what it has to say. Let f of x equal g of x, two different functions that are equal, for all real numbers in an open interval containing c, except, notice, that at c, f of c does not equal g of c. These functions are just alike except at that one point. The theorem goes on to say if the limit of g of x exists as x approaches c, then the limit of f of x also exists as x approaches c, and the two limits are equal. We're going to be using this theorem as we learn some algebraic or trig techniques to rewrite functions so that we will be able to evaluate our new function by direct substitution. Let's take a look at our first example. If it exists as x approaches 2, x squared plus x minus 6 over x minus 2. Now, I want you to notice, if we try direct substitution here, if x is 2, notice if I substitute a 2 right here, 2 subtract 2 gives me 0. And so that's going to be a problem, isn't it? We cannot do direct substitution. Now, what we're going to do here is our first technique using algebra, and that is to use cancellation, which simply means we're going to see if we can factor and do some canceling. So let's take a look at this problem. Now, I'm not evaluating the limit just yet, so I'm still going to write limit as x approaches 2. Recall, this is instructions for me, and until I actually find the limit, I'm to keep writing that. But what I want to look at is this trinomial in the numerator. Notice that we can factor x squared plus x minus 6 into x plus 3 times x minus 2. I'm going to go ahead and put that denominator in parentheses just so those factors are a little bit more easily seen. Now, you're used to doing this in algebra, aren't you? You factor, and if you have a common factor, you say that you divide the numerator and denominator by that same value, and you cancel those out. Now, I want to talk about that a little bit before we move on and actually evaluate this limit. Notice that if x is 2, we would be dividing by 0 here, which is not allowed. So we can't just divide or cancel that factor out unless x is not exactly 2. Now, if x is approaching 2, it just says x is very close to 2, but it's not equal to. Now, when we actually cancel these factors, we have created a new function. The new function simply contains x plus 3. Now, these two functions are not exactly equal. This function is defined when x is 2. This function is not defined when x is 2. Do you see the difference? However, they agree at every point except x equal 2. And so this is where that theorem is coming in that we talked about earlier. These two functions agree everywhere except at x equal 2. Now, our new function that we have right here has a limit that we can evaluate by direct substitution. If x gets very close to 2, then x plus 3 is going to get very close to 2 plus 3, or 5. So, appealing to our theorem, since the limit of this function is 5, the limit of this function is also 5 as x gets close to 2. So our first technique that we've illustrated here is to create a new function that is exactly like the old one except at that one value, and then find the limit of our new function. And we accomplish that by factoring and canceling. Find the limit if it exists. The limit as x approaches negative 3. I don't know if that negative is showing up very well on your screen. X approaches negative 3. X cubed plus 27 divided by x plus 3. Notice again, if we try to substitute a negative 3 for x, negative 3 plus 3 gives me a 0 down here in the denominator, which is undefined. Now, while we're here, I might also illustrate to you that if we put negative 3 in the numerator, I would have negative 3 cubed is negative 27. Negative 27 plus 27 is also 0. Now, some students make the mistake of saying if they have 0 over 0, that's 1, just like 2 over 2 is 1. However, that is not true. Recall, if you have a 0 in the denominator, it's not defined no matter what is up here. This form of 0 over 0 is sometimes referred to as an indeterminate form when we study limits. Indeterminate simply means we cannot tell in this form right here what the limit of this function is. So we're going to need to rewrite it. So recall, 0 over 0 is not 1, nor is it 0. Okay? It's undefined. So we're going to attempt to do this factoring and canceling technique like we looked at in the first example. So again, I'm going to write limit as x approaches negative 3 until I'm ready to find that. Do you recall how to factor a sum of two cubes? This is x cubed plus 3 cubed. The sum of cubes formula, if you've forgotten that from algebra, says that your first factor contains the cube roots of these and has the same sign. So the cube root of x cubed is x, the cube root of 27 is 3, and since that's a plus, our first factor will be x plus 3. Now, the second factor is found by looking at this factor we created down here. You square this first number, that would give me x squared. This sign is always the opposite of this one, so it would be a negative. Then ignoring this sign, you multiply 3 times x, that's your middle term here, and then finally you square this 3 and get a positive 9, and that's the second factor. you might want to recall from algebra that you can factor both a sum and a difference of cubes by that process. Now, notice again, by doing this factoring, we have a common factor. So if we cancel this factor, we're assuming our x value is not negative 3 because we'd be dividing by 0. But we cancel that factor and we create a new function that agrees with our old one everywhere except at negative 3. And of course, our new function just contains x squared minus 3x plus 9. And as before, this new function can have its limit evaluated by simply direct substitution. Now here's where I quit writing limit because I'm actually finding the limit. I'm going to substitute negative 3 for x. So if I square negative 3, I get positive 9. And if I put a negative 3 here, negative 3 times negative 3 is another positive 9. And finally, I'll bring down my plus 9. And 9 plus 9 plus 9 is 27. So the limit as x approaches negative 3 of x cubed plus 27 divided by x plus 3 equals 27. And again, it's because the limit of this function is 27, and these two agree at all but that one point, and therefore they have the same limit. One thing you might consider doing after one of these problems, if you have a graphing calculator, graph one of these functions and sort of investigate what's happening. Like for instance, this last one we did, you can use your little trace key there and see what's going on right at x equal negative 3, and I think you'll find that we do have the correct limit. Find the limit if it exists. The limit as x approaches 0, square root x plus 4 minus 2, all divided by x. Notice again, I can't substitute because I would get a 0 in the denominator. Okay? I might point out as well here, if x is 0, you have the square root of 4, which is 2, minus 2 is also 0 in the numerator. This is another one of those indeterminate 0 over 0 forms. Now obviously with this one, we cannot factor and cancel. And so we're going to do another technique that we call rationalization. Now, you might recall if in a trig class that you rationalized denominators. Well, sometimes when we're evaluating limits, we want to rationalize numerators instead of denominators. So I've recopied my function exactly like it is, and we're going to multiply this by the square root of x plus 4 plus 2 over itself. Now, a couple of things I might want to point out to you here. First of all, I'm multiplying this fraction by 1, the same thing over itself, and so I'm not actually changing the value of this fraction, I'm just changing its form. You might also recall from trig that these are referred to as conjugates. They're just alike. They're two binomials, so to speak, just alike except for the sign here. Now, let's go ahead and do this multiplication, and I'm going to show you what will happen. Now, remember, I keep writing this limit until I actually evaluate it. I know that's a nuisance, but it's very important that we keep in mind what we're doing. Okay, up here, if we multiply the first terms together, the square root of x plus 4 times the square root of x plus 4, we simply get x plus 4, don't we? Now, this is why we wanted to use conjugates. Notice your outside product is 2 times the square root of x plus 4. Your inside product is negative 2 times the square root of x plus 4. So that inside and outside product will cancel each other out and be a 0. And then finally, when you do the last two terms, you get a minus 4. So our numerator becomes x plus 4 and then minus 4. Now, in the denominator, I'm going to not multiply this out, but I'm going to simply write x times this quantity, x plus 4 plus 2. You'll see in a second why I'm choosing not to multiply that out. Okay, again, I'm going to rewrite this limit thing. Notice in the numerator, the plus 4 minus 4 adds to 0, and so we're simply left with x. In the denominator, we have x times the quantity, square root x plus 4 plus 2. Now, if you'll notice what we've created in this new form is we now have a common factor that we can cancel out. So if we cancel these x's, then our new function that we're creating here will have a 1 in the numerator, and in the denominator it will simply have the square root of x plus 4 plus our 2. Now, going from this step to this step is where we have created a new function that agrees with the old one except at x equals 0. Okay? Now, notice our new function. We can now substitute a 0 for x in this new function. I'll have a 1 in the numerator, and if x is a 0, I have the square root of 4 plus 2, which gives me 1 over 2 plus 2, or 1/4 for my limit. So this technique uses rationalization. We rationalized our numerator. That simply means that we got rid of our square root in the numerator, and doing that gave us a common factor that we could cancel and create that new function. Find the limit as x approaches 0 of x plus 3 quantity squared minus 9, all divided by x. Again, do you see why we can't substitute right now? I would get a 0 down here. Now, this one is not in a form where we can factor and cancel. It is also not in a form where we can rationalize, but you'll notice there's some algebra that we can do. This is a binomial that we can actually square. So we're going to do the algebra and see what happens with this thing. If I square x plus 3, remember that means to multiply x plus 3 times x plus 3. We have x squared plus 6x plus 9. I might remind you the shortcut. Square the first one, multiply these two together and double the answer, and then square the last one. And then notice I have the minus 9 that I'll bring down, and in the denominator I have x. So all I've done is multiply this out. But notice that by doing that, I have a 9 minus 9 right here. So those are going to add to 0, leaving me x squared plus 6x divided by x. Now I can factor the numerator. So I will factor an x out of those two terms, leaving x plus 6 as the second factor. And at this point, we again have a common factor that we can cancel out. We'll cancel out those x's, create a new function that agrees with the old one except at x equals 0. And this new one we can do by substitution. 0 plus 6 gives me 6 as my limit. So here it just meant, it actually just amounted to doing some algebra, multiplying out our binomial, some things canceled out, then we were able to factor. This problem is similar. Find the limit if it exists. H is approaching 0. I have x plus h cubed minus x cubed over h. Notice I can't substitute a 0 for h yet. But the similarity here is that, again, I have a binomial with a power, and I can do that power. Now, you may or may not remember the shortcut way of cubing a binomial. I'm going to put it down and remind you. You cube the first term, that would give you x cubed. And then if that's a plus sign, all your signs are plus. So I'll put a plus. Your coefficient is a 3. You square the first one, x squared times the second one, x squared h. Then you have another plus sign. Again, your coefficient is 3. This time, this is to the first power, and you square h. So ax h squared. And then finally, you cube the third term. If you need to review that from algebra, you might want to go do that. Now, we will subtract the x cubed, bring it down. All of this is over h. Now, let's see what happens when we start simplifying what we have. I have x cubed here minus x cubed here. Those x cubes are going to cancel. That leaves me 3x squared h plus 3x h squared plus h cubed all over h. Now, the good news here for me is that now every term in my numerator has an h, and so I can factor out h in the numerator, leaving 3x squared plus 3xh plus h squared all divided by h. And you see we're now again at that point where we can cancel this common factor of h. And of course what that does is it eliminates the problem. It creates a new function, but it eliminates the problem that I had in terms of being able to evaluate this with direct substitution. I no longer have that denominator to become 0. So now we can substitute a 0 for h. Notice that's for h. There's no h in the first term, so that will stay 3x squared. If I substitute a 0 for h in the second term, I get 0. 3x times 0 is 0. And finally, in the last term, 0 squared, of course, is also a 0. So simplifying that, my limit is 3x squared. Remember, a limit does not always end up a number if you have two variables up here. H is the one that is approaching 0. We're not told anything about the value of x. Well, let's look at another type of problem. The limit as x approaches 0. I have 1 over x plus 3 minus 1/3 all divided by x. Again, notice I can't substitute 0 for x or I would get a 0 in the denominator. Now, this is a complex fraction. So we're going to simplify this complex fraction, and there's more than one way to do that. I'm going to do the technique that I personally prefer, but there are other ways that you could also do this. What I like to do is take the numerator and denominator of my complex fraction here and multiply them by the same thing. What I'm going to choose here is 3 times x plus 3. The reason you might see is because that's the common denominator up here. So when I distribute this times my first fraction, the x plus 3 would cancel, wouldn't it? And I would have 1 times 3. Let me get this limit written down because I'm still not ready to do that. So remember, x plus 3 canceled. I have 1 times 3 is a 3. Now subtract. When I do the second fraction times this, the 3's cancel, and I have 1 times x plus 3. Now I'm going to be careful here because notice I'm subtracting that whole thing, so we need to use a parenthesis there. And then on the bottom I have x times 3 times x plus 3. I'm going to write that as 3x times x plus 3. Now that has gotten rid of my complex fraction, and let's do a little more simplifying. If I distribute my negative, 3 minus x minus 3 over 3x times x plus 3. Continuing to simplify, notice in the numerator, 3 minus 3 is 0. So I have negative x over 3x times x plus 3. Now finally, we're at a point where we have a common factor of x that we can cancel out. So we're finally creating that new function that agrees with the old one except at that one value. The numerator is now negative 1, and in the denominator I have 3 times the quantity x plus 3. So we simplified our complex fraction, got it into a more simple fraction format, just continued to do the algebra, and finally we were able to cancel that common factor. Now we can do our direct substitution here. The numerator is negative 1. In the denominator I have 3 times the quantity 0 plus 3. Of course, 0 plus 3 is a 3, so 3 times 3 is 9. Negative 1/9 is my limit. Here's an example using trig functions. Find the limit if it exists. The limit as x approaches pi over 2 cotangent x divided by cosine x. Well, let's see what the problem is. Pi over 2. If I substitute pi over 2, do you remember what the cosine of pi over 2 is? If it's been a while since you've done trig, you may have forgotten, but think about the graph or your special values. That's a 0, so I cannot substitute a pi over 2 for x. Now, of course, this is not like the algebra equations or limits that we were looking at earlier. This is trig functions. But with trig functions, sometimes we can also rewrite these using trig identities. So I'm going to look at that possibility. Do you recall that the cotangent of x is the cosine of x divided by the sine of x? So I'm going to replace cotangent with cosine over sine. And then I've got cosine x down here in the denominator. Now again, I've got a complex fraction now. So as I did earlier, I'm going to multiply the numerator and denominator here by the sine of x to simplify that complex fraction. So in the numerator, of course, these cancel, leaving cosine x. In the denominator, I have cosine x times sine x. And what has happened here? Well, back to what we were doing with the algebra, I now have a common factor that I can cancel. So I will be looking at a 1 over sine x. So we're still using that same theorem basically. It's just that we have trig functions here. Finally, I can do my substitution. 1 over the sine of pi over 2. Recall that the sine of pi over 2 is a 1. So 1 over 1 is going to give me a 1 for the limit of this function. Now, before we look at another example, I want us to look at another theorem called the squeeze theorem, which is going to help us to prove a couple of special trig limits that we will also use sometimes when we evaluate limits involving trig functions. Let's take a look at what this theorem says. H of x is less than or equal f of x is less than or equal g of x for every x in an open interval containing c except possibly at c itself. Now let's stop right there and talk about what this is saying. I have three functions here. Notice f is always between g and h. Now I might just sort of show you, I don't know what particular functions necessarily, but according to this function, h is our smallest function. So let's say we've got a graph here. This is h of x, and then I'm going to kind of flip back over here. F is in the middle, and g is the biggest one. So up here somewhere would be g of x, and your f of x is in between here somewhere. Now, let's take a look at what the theorem says when we have this setup. If the limit as x approaches c of h of x is L, and that's also the same value as the limit as x approaches c of g of x. Now let's look. H was the one on the bottom, g was the one on the top, and these two, as we approach some number c, is the same thing. Then it says the limit as x approaches c of f also has to be L. Now, in terms of a diagram, here's what we're saying. If h is coming along and it approaches some y value L, and g comes along and approaches that same L value, if f is always between those functions, it has to come in toward that same value, doesn't it? That's what the squeeze theorem is telling you. Now, I'm not doing a formal proof here, but just sort of letting you understand what that theorem says, because we're going to use it in a second. We are going to prove this. Prove that the limit as x approaches 0 of sine x divided by x is equal to 1. Now, I want you to just look at this a second. Sine of 0 is 0. This is 0. 0 over 0 is indeterminate. It is not equal 1, although as it turns out for this example, we do end up getting 1 as a limit. I want to remind you that all of these other examples that we've just looked at had 0 over 0 starting out, but we got all kinds of different answers, not just 1. So this is one of the few times when that does happen. We want to actually prove that this is true. And the way that I'm going to do that is to use a little bit of information from trig, so we might be reviewing that a little bit. Now, I'm going to do just a little bit of a rough sketch here. Let's say that we have part of a circle here, and the radius of this circle we're going to say is 1, okay? Now, I've extended sort of a radius out to the edge of that circle, and from that point on the circle, I'm going to drop a perpendicular down to the x-axis, okay? I'm going to call from here to the foot of that perpendicular x, and I may not have enough room for you to see this very well, but this perpendicular line right there, I'm going to call y1. Okay, I know you can't read that very well because it's so small, but I'll refer back to it and so you won't be confused. Now, here, where my circle comes down and hits the x-axis, I'm going to also do a perpendicular up and extend this radius out until it meets and create another triangle. And from here up to here, I'm going to call y2. Now, since I went all the way from here to the edge of the circle, this distance is a 1. Now, what I want you to see here is I have a small triangle right here. I have a large triangle right here. And in between those, do you see where that part of the circle comes over? This pie-shaped part is a sector of a circle. So what I'm telling you is that I have a small triangle. The area of the small, I'm just going to abbreviate, SM triangle, will be less than or equal the area of the sector of the circle, and that in turn will be less than or equal the area of my large triangle. You see the sector right in here? The small triangle is completely inside it, so its area has to be less, and the big triangle completely encloses that sector, so it will have a larger area. Now, we know that the area of a triangle is 1/2 base times height. So on this small triangle, using the x as the base and the y1 as the height, my area is going to be 1/2 x times y1, less than or equal. Now, do you recall from trig how to get the area of a sector of a circle? It's 1/2 r squared theta. Okay, I'm just going to leave it in that form right now, where theta is an angle in radians. Okay? And then less than or equal the area of my large triangle, 1/2. Now my base of my large triangle is 1, but the height is y2, y sub 2. Do you see how we've set that up so far? Now, I might just remind you right here that r is a 1, so that's going to be a 1 squared. Now, I've set up an inequality here, and all of them, notice, have the 1/2, so I can multiply through by 2. That will not change the direction of my inequalities, but it will simplify what I have to x times y1 is less than or equal, just theta here, is less than or equal y2. Okay? Now, let's talk about some trig functions. Theta is this central angle right here in our sector of our circle. Look at your small triangle. Okay? Notice that the cosine of angle theta using your small triangle would be x over the hypotenuse of 1, x over 1. So x is equal to the cosine of angle theta. Okay? Now, notice, looking at the large triangle, that the tangent of angle theta using the large triangle would be the side opposite, which is y2, over the side adjacent, which is 1. So y2 is equal to the tangent of theta. Okay? Now, finally, if I go back to the small triangle, the sine of angle theta, using the small triangle is the side opposite, which is y1, over its hypotenuse, which is 1. Do you see those? Now, we're going to do some substituting here. In place of x, I can put cosine theta. In place of y1, I can put sine theta. Less than or equal theta, less than or equal y2 is the tangent of theta, and I'm going to put that in the form of sine theta divided by cosine theta. Okay? I just wrote tangent as sine theta over cosine theta. Now, I'm going to divide everything here by the sine of theta. As long as I'm in the first quadrant here, the sine of theta will be positive, okay? And so I'll be dividing by a positive value, and these inequalities will not change direction. So dividing by sine theta, I get cosine theta is less than or equal
theta divided by sine theta. And dividing this by sine theta, I get 1 over cosine theta. Okay? Now finally, one more step. I'm going to invert these, flip them over. You might recall from algebra, if you invert these, your inequalities change direction. So that's going to change to greater than sine theta over theta, greater than or equal cosine theta. Okay? Now, here's what I want to think about. We're going to think about the limit as theta approaches 0. Now, if I have 1 over cosine theta, well, the cosine of 0 is 1. That's 1 over 1 equals 1. Okay? So this function is approaching 1 as theta gets close to 0. Well, this one, the limit as theta approaches 0 of just cosine theta, is cosine of 0, which is 1. So this one also is approaching 1. Okay, this is always between these two. These two are getting close to 1, so where does that one have to go? According to the squeeze theorem, this one also has to get close to 1, doesn't it? Now, I proved this using theta, but the variable is unimportant. What I have shown you is that the limit as theta approaches 0 of sine theta over theta equals 1. This is saying the same thing. It's using an x everywhere that we have a theta, so it's telling you the same thing. So you want to sort of put this down as one of the things that you want to remember because it comes in very handy. A couple of things. It's sine x divided by x. X must be approaching 0. This is only true if x approaches 0 that we get a 1 here. Okay, I have a second one that I want to prove. Prove that the limit as x approaches 0 of 1 minus cosine x divided by x is equal to 0. Now I want to show you again, notice if x is 0, our denominator is 0, the cosine of 0 is 1, 1 minus 1 is 0. Here I have a 0 over 0 like we did a while ago, but our limit is not 1 this time, it's 0. So that's, remember, is indeterminate. You can't tell from that form. Okay, well let's see what we can do on this one. I'm going to apply sort of a little trick. It's not really a trick, it's just a little manipulation, change of form. I'm going to take this and multiply by 1 plus the cosine of x in both numerator and denominator. You might recall doing this sometimes when you proved limits in trigonometry that you could do this. Again, remember, I'm multiplying this by 1 in this form, so I'm not really changing its value. But if we notice conjugates here, multiply, we have 1 times 1. The outside and inside products will cancel out, and I'll have a minus cosine squared x. In the denominator, I have x times 1 plus cosine x. I'm going to leave it in that form right there. Now, what do you know about 1 minus cosine squared x? Do you remember from trig what you can do with that? 1 minus cosine squared is equal to sine squared, isn't it? So I'm going to substitute that in. That's just using an identity, so we're still equal to the same function that we had before. But what this is going to allow me to do is to do a little bit of rewriting. Sine squared x means I have sine x times sine x. So I'm going to write this like this. Now notice I've got sine squared x up here, and I have x times 1 plus cosine x. So these are still equal. But here's why I wanted to do that. Look at this thing right here. X is approaching 0, and I have sine x over x. We just proved, what about that? That that's equal to 1. So I can just substitute a 1 there. Substituting a 0 for x here, I have the sine of 0 over 1 plus the cosine of 0. Now this is real important that you understand this. The sine of 0 is 0, but the cosine of 0 is 1. So I have 1 times 0 over 2. Now this is not undefined, it's just simply 0. And so I have 1 times 0 is 0. So I have proven now that the limit as x approaches 0 of 1 minus cosine x divided by x equals 0. Now I've put these on a screen for you that I've labeled two special trig limits. X must be approaching 0 in both of these. The first one has sine x over x. That limit is 1. The second one has 1 minus cosine x divided by x. That one is equal to 0. I always recommend that my students memorize these two special trig limits because they come in so handy when we're evaluating limits involving trig functions. Let's look at this one. Find the limit if it exists. Limit as x approaches 0 sine 2x divided by x. Now this is not exactly like that special trig limit. Let me put this back up here and let's just make this clear. Notice this says sine 2x, this says sine 1x. So those are not exactly alike, are they? But let's remember that in trig we learned an identity called one of the double angle identities for the sine of 2x. Do you recall that one? The sine of 2x is 2 times the sine of x times the cosine of x. So I'm just going to use that identity to rewrite sine 2x. Now, here's what I'm looking for. Do you see that thing right there? That's our special limit. So let's rewrite this in this form. I'm going to have sine x over x times 2 cosine x over 1. Do you see that? That's 2 sine cosine in the numerator, x in the denominator. This is our special trig limit here. X is approaching 0, so that will approach 1. And notice here we have 2 times the cosine of 0. Well, since the cosine of 0 is 1, that's 2 times 1 or 2, and so our limit will equal 2. So again, we appealed to that special trig limit that we proved a second ago. Find the limit as x approaches 0. I have secant x minus 1 over x times the secant of x. Now, again, I can't substitute. Do you see if I put a 0 for x, automatically this is 0 down here. This doesn't look like either of those trig limits that we proved a second ago, but let's see if we can do some rewriting. What do you know about secant x? Secant x is 1 over cosine x, isn't it? So I have 1 over cosine x minus 1. In the denominator, I have x times 1 over cosine x. Now, that's created a complex fraction. So like we did earlier, I'm going to multiply the numerator and denominator here by the cosine of x to simplify that complex fraction. Now, the cosine of x times this first term, they would cancel and leave me 1 over 1, just that. Minus 1 times cosine is minus cosine x. In the denominator, these would cancel out, leaving me x times 1 is x. And look, this looks exactly like that special trig limit we proved. X is approaching 0, 1 minus cosine x over x, and we showed that that is a 0. One final example here. Find the limit as x approaches 0, tangent squared x divided by x. Again, you can't substitute. So, let's see what we can do with this one. You might be thinking ahead of me maybe by now. What do you know about tangent? Sine over cosine? Let's put that in. I have sine squared x over cosine squared x, and that's being divided by x, isn't it? Okay, we replace that with sine squared over cosine squared. Now, like we've done before with these complex fractions, I'm going to multiply the numerator and denominator, this time by cosine squared x. These cancel, so I have the limit as x approaches 0, sine squared x, since those canceled, and down here I have x times cosine squared x. Now, with one more simple rewrite, we're going to have one of those special trig limits. Sine squared means I have sine x times sine x. In the denominator, I have x times cosine squared x. Do you see I've split that up? I still have sine squared over x times cosine squared, but I have it in a new form. The reason is for that. X is approaching 0, sine x over x, I know that goes to 1. And here I have the sine of 0 over cosine squared 0. Well, again, the sine of 0 is 0, but the cosine of 0 is 1, so 1 squared is 1. Again, it's important to note that that's defined. I don't want to have a 0 over 0 here. 1 times 0 equals 0 for that limit. Now, I finally put sort of a summary of techniques here. Cancellation, we use that over and over and over. Sometimes we had to do a little work to get it in that form. Basically, look at it and see if you can factor and cancel. Rationalization, remember that one example we did where we rationalized the numerator. Sometimes you possibly might want to rationalize the denominator as well. Do any obvious operations. I put like add, multiply, where we could square those things or cube those things or get common denominators, maybe add things. Use identities when it comes to trig functions. And then finally, use those special trig limits that we had. Now, this completes our lesson on evaluating limits. So I hope that you've seen some ideas of things that you can use. Overall, all of these started out being in an indeterminate form. In particular, that 0 denominator that we had to do something with. But we were able, through these various techniques, to get into a situation where very often we could cancel out that troublesome factor, creating a new function that agreed with the old one except at one point, and then appealing to that theorem, we could evaluate the limit. And of course, we also saw those special trig limits and how useful they were. This completes your lesson on evaluating limits.